Okay, but considering the total number of students is around 220 and we are having only around 20 or something, it's not good. Anyway, so let me share the whiteboard. Is it visible to everyone?
Yes, sir.
So I am just copying the question to the whiteboard. Then we will discuss. So in this tutorial, there are two questions are there. Okay, so in the first question, what is been given is there is a 6-meter cube polymerization reactor is there. So maybe I'll just draw it for you so that you will appreciate what I'm trying to say. Just a minute. Okay. So what is been given in this particular problem is there is a 6-meter cube volume polymerization reactor is there. So maybe we can take this polymerization reactor something like this. Okay, this is, let's say, a polymerization reactor is there. Okay, and this particular polymerization reactor, in this particular polymerization reactor, 5-meter cube of monomer at 24 degrees Celsius is charged. So initially the temperature of the monomer is Ti is just equals to 24 degrees Celsius. Okay. The charge has to be heated to 80 degrees Celsius. So Ti is 24 degrees Celsius, but what we wanted to do is ultimately we wanted to heat this monomer charge to the final temperature of 80 degrees Celsius. Okay. Before the initiator is added to the added to start the reaction. The liquid in the reactor is well stirred and the liquid side heat transfer coefficient is 400 watt per meter square. So here HI which is inside is 400 watt per meter square degree Celsius. Okay, this is what the inside heat transfer coefficient is there. Then what is been given is hot oil flows through the jacket at a sufficiently high rate and the average oil temperature is 125 degrees Celsius. So there is a outside, there is a jacket is there. Okay. Outside there is a jacket is there. So hot oil is continuously being circulated through this, and we are assuming that the temperature of this hot oil here is okay, maybe I'll just use this. Okay, let me use this just as a T. So final temperature I'm interested in this TF, whereas the oil temperature T naught here is, let's say, T naught is 125 degrees Celsius. 125 degrees Celsius. Correct. Again, the outside heat transfer coefficient is given. The oil side heat transfer coefficient is 300. So H oil is given, that is 300 watt per meter square degree Celsius. Okay. this area here, remember this is the heat transfer area, isn't it? This is what the heat transfer area is going to be, correct? So this area is given as, this area is given as 10 meter square, isn't it? So heat transfer area A is given as 10 meter square. 10 meter square. Okay. Calculate the overall heat transfer coefficient and the time required for heating. So we wanted to calculate the U first, and then we wanted to calculate the final time TF. This is what we wanted to calculate in part 1. In part B, the relevant properties of the monomer are given here. So density of the monomer is 870 kilogram. Okay. So rho m is given. Rho m is given as 870 kg per meter cube. Cp is given. Specific heat is given as 1.81 into 10 raised to power 3 joule per kg per degree Celsius, isn't it? And thermal conductivity is given. Thermal conductivity of the monomer is given. So that is given as 0.25 watt per meter per degree Celsius. Okay. So again, based on this, we have to estimate the liquid film thickness. So liquid film thickness, remember liquid is inside here. So this particular film thickness here, which is delta M, we need to calculate. Okay. So this is part A, this is part B. In part C, what we need to calculate is, in part C is for same HI, sorry, for same delta M, what will be HI if monomer is replaced by water. So is question clear to everyone? Hello? Is it clear to everyone?
Yes, sir.
So inside
in
the
this
container,
case, is there any
inside
question?
the container, sir.
Yes, Aditya, please go ahead.
So is it the monomer inside the container, or what is, because the monomer is 5 meter cube and the container is 6. So is the container empty or what?
Okay, so see, monomer is 5 meter cube. That means it's partially filled. Do you fill the entire reactor completely, or you keep some space available above?
Acha, for the spilling part, like for that purpose.
So this is what this entire thing is 6, but the monomer is charged only up to 5 meter cube. Okay.
Okay. Yes, sir.
Okay. All right. So now let us start with this problem. So in this case, first we have to calculate U. Now in this case, what is been given is, if you look at the problem here, see here outside H0 is there, which is nothing but this 300 watt per meter square, isn't it? Inside the heat transfer coefficient is 400 watt per meter square, and also there is a metal wall in between, isn't it? But since this metal wall is there, we can neglect the heat transfer resistance offered by this metal wall in between. Do you all agree? Yes or no?
Yes, sir.
Yes, sir.
And another thing is,
Sir, can you repeat one thing? Sir, can you repeat?
okay, so what I'm trying to say here is, since in this case we need to find out the overall heat transfer coefficient, because there is convection which is taking place inside this fluid which is there inside the container. Also there is a convection outside here in this jacket, isn't it? And there is a conduction taking place through this metal wall which is in between. isn't it? So in such cases, we in general write the equation in terms of overall heat transfer coefficient, if you remember last class, isn't it? So we need to calculate the overall heat transfer coefficient. So overall heat transfer coefficient depends on all three resistances. So resistance here outside the container here is this H naught, isn't it? The resistance inside will be with respect to this Hi, and also there will be resistance for the metal wall. But metal wall, since metal wall will have a very high thermal conductivity, isn't it? And also this thickness of this metal wall is not very high, isn't it? So we can neglect the resistance offered by the metal wall here. Do you all agree?
So sir, we are implementing lumped heat capacity concept. Lumped heat capacity.
No. We are not saying anything about lumped capacity here. I am saying that the metal wall is separating both the fluids.
Like you said that metal wall has high.
See, I am saying that there are three resistances offered. One is the convective resistance outside the container, which is surrounded by the jacket fluid. There is a convective resistance inside the container where the liquid monomer is present, and there is a conductive resistance which is separating both the liquids, isn't it? In the metal wall. Now I am saying that since the metal wall will have a very high thermal conductivity with respect to the hot oil as well as the monomer which is there inside, isn't it? And also the thickness of the metal wall is not very high, isn't it? Correct. So we can neglect it. We can neglect this resistance. Do you all agree?
Yes, sir. Yes, sir.
So our equation will simplify. If you remember the overall heat transfer coefficient expression which we have looked at in our last class, that will get immensely simplified, isn't it? So if I can write down the expression in such cases, let me just scroll a little bit up. So in such cases, overall heat transfer coefficient 1 by Ui, if I represent in terms of the inside surface area, that can be written as 1 by Hi plus Ai ln R naught by Ri divided by 2 pi K Kw and L, isn't it? Plus Ai by A naught 1 upon H naught. If I represent in terms of inside surface area, if I represent U in terms of outside surface area, then it becomes A naught by Ai 1 by Hi plus A naught ln R naught by Ri divided by 2 pi KWL, and this becomes A naught by Ai. Sorry, this becomes just 1 by H naught, 1 by H naught, isn't it? Now, if we take these assumptions, conductive resistance is negligible. This is the first assumption, and second assumption is thickness of the reactor vessel compared to very small compared to its diameter. So in both these cases, the above equation gets simplified as 1 by U as just 1 by Hi plus 1 by H naught. Do you all agree? Do you all agree or not? See, so conductive resistance negligible,
Yes, sir.
that means this middle part will goes away, isn't it? And since we are taking that the reactor thickness is, basal thickness is very small. That means the outside surface area and inside surface area both are nearly the same. So we can take this AI by A naught is also same as just equals to 1. So we can simplify this both these equation as 1 by, okay, so this could be 1 by UI, just a minute. This could be 1 by UI or 1 by U naught. Both are same as 1 by U. Do you all agree? Yes or no? Hello?
Yes, sir.
Yes, sir.
So with this assumption, now let's put the values. So 1 by U is given as 1 upon HI is given as what? How much is the value of HI? HI is 400 and H naught is 300. So from this we get U as, U comes out to be, anyone? It comes out to be 171.4 watt per meter square per degree Celsius. Check whether it is correct. Is it correct?
Yes, sir.
So this is the answer for part A. Now in part B, what we wanted to find out is the time required for reaching to the temperature of 80 degrees Celsius from the starting temperature of 24 degrees Celsius. Correct? Isn't it? So in this case, the balance equation is going to be what? Balance equation will be the rate of change of energy of the monomer content will be equals to the heat transfer, isn't it? Total heat transfer by the oil, isn't it? So we can write down this as MCP dt by dt is should be equals to UA T naught, which is nothing but the oil temperature minus the actual temperature of the monomer mass. Do you all agree? Yes or no? Is it clear? This part?
Could you repeat this part once more, please?
So whatever the, okay, let's go the system. Okay. So remember initially the monomer temperature was 24 degrees Celsius, but this jacket fluid is at the 125 degrees Celsius. So what will happen eventually, the heat will be transferred from the jacket fluid to this monomer, isn't it? Again, this jacket fluid is continuously circulating with a high flow rate. So therefore this temperature outside in the jacket always remains at 125 degrees Celsius, whereas the inside monomer temperature is going to increase from 24. Do you agree? Yes or no?
Yes, sir.
And eventually we wanted to find out the time TF when the temperature of this monomer which is inside this container will increase to a 80 degrees Celsius, isn't it? So we wanted to find out that particular time. Do you all agree?
Yes, sir.
So what will be the balance in this case? The rate of change of energy of this monomer mass which is inside this reactor should be equals to the amount of heat added by this, isn't it? Amount of heat added by the hot fluid here outside the jacket, isn't it?
Yes, sir.
So that is what we have equated. So amount of heat transfer, this is the amount of heat transfer should be corresponding to the rate of change of energy inside this monomer, isn't it?
Got it. I confused the two equations or something. I'm sorry.
So now in this case, what will be the mass of monomer? Mass of the monomer will be volume of the monomer into its density rho m into Cp dt by dt, isn't it? And that will be U, we have already calculated, that is 17. Okay, maybe we just keep it in terms of this UA T naught minus T, isn't it?
Yes, sir.
Correct. So this is the same equation which we have seen several times. So if we
Sir.
integrate,
Sir.
yes, please go ahead. Yes, please go ahead.
Sir, one thing I want to ask, like this, we have assumed
Your voice is not clear,
the
Achintya.
water is high. So So this would be given in the question, or we have to make the assumption?
Which assumption you are saying?
So the assumption that we take that the thermal conductivity of the wall is very high and the thickness
So
of the
it is
wall is
already, see
negligible.
here what we are looking at, what this system is. This system is basically you are having a container, isn't it? In the problem, what is been given is there is a reactor, isn't it? So reactor will be definitely made up of some metal. Why it should be metal? Because there is a outside jacket from where the heat is being transferred, isn't it? So that means you will have a metal, you will not have a plastic reactor, isn't it? Because you want that heat transfer to occur. Correct? Yes or no?
Yes, sir. Yes, sir.
So that means you will use a material which will have a very high thermal conductivity because it should facilitate heat transfer. Correct? Yes or no? Hello? So that means this assumption which we are making is a realistic assumption. We are not saying that it is unrealistic. It is a realistic assumption. Do you agree or not?
Yes, sir.
If I
Yes,
say,
sir.
if I go back to the system, yes, you can argue that why we should take this as a metal container. Why should not? Why we should not take this as a plastic container? If we take a plastic container, will there be a heat transfer from the jacket fluid to the fluid which is inside the reactor? It's not going to facilitate that because plastic being a thermal insulator, it's not going to facilitate the heat transfer. So obviously, the reactor should be made up of such a material which should facilitate heat transfer, and for that definitely one should use the reactor made up of metals, isn't it? Correct? Yes or no? And when we are saying this reactor is made up of metal, that means the thermal conductivity of the metal are always 1 or 2 degrees magnitudes higher than the liquid, isn't it? So both here inside this container and
Yes,
outside
sir.
this container, the liquid is present. So that means the resistance offered by this metal wall is going to be much lower. And typically, see, all this data which is given here is for polymethyl methacrylate. Okay, so methyl methacrylate monomer you are charging here inside. So if you look at the melting point of methyl methacrylate, that is polymethyl methacrylate is around all right, sorry, this is not for PMMA. Here this is for nylon 6 production. So nylon 6 is produced from what? It is produced from epsilon caprolactam. Epsilon caprolactam is you will see that starts melting around 80 degrees Celsius. So initially you wanted to hit this material here. Okay, all right, and then you add the initiator. So that is the typical example I am giving,
Yes, sir.
but it is not been specified here. Okay, in this problem it is not been specified that I'm giving you a usual practical application. So typically you add the monomer when the entire polymer or a monomer mass is melted. Okay. Okay. Is it clear? Is it clear?
Yes, sir. Yes, sir.
Okay, but that part
Yes,
is
sir.
not been given in the problem. Okay. So, and that is not needed also. Coming back to the question from Achintya that why we are taking this as a metal, because typically we wanted to facilitate heat transfer, and that can be done only by using the metal container. So that's why metal is used. Why we are ignoring the resistance? Because the metal will have at least 2 order of magnitude higher thermal conductivity compared to the liquid, and therefore it is safe to assume that the resistance offered by the metal wall is negligible. Another assumption that why we are taking that the thickness of the reactor vessel is very small, but typically if you look at the reactor, the diameter of the reactor will be in meters, whereas the thickness of the reactor will be in or maximum in cms, isn't it? So clearly the reactor thickness is also very small compared to the diameter if you look at the real life reactors. So typically in a real life reactor, you use the monomer mass around 10,000 kgs or something. Okay. So considering that, the second assumption is also a reasonable assumption. Is it clear to everyone now? Hello?
Yes, sir.
Yes,
So
sir.
with this, then we can, we have already seen this equation. So what type of equation we are expected to get in such cases? In such cases, if you rearrange this and, if you rearrange this equation number 1 and integrate, what you are going to get is basically you are going to get T naught minus T divided by T naught minus Ti, and that should be opted as exponential of minus UA MCPT. Isn't it? This is what you are expected to get. Yes or no?
Yes, sir.
This we have already derived these equations earlier. If you remember your class notes or whatever we have covered in the class, if you remember that this equation we have derived several times. Okay, so we can take this T naught minus T on this left hand side, so dt divided by T naught minus T, that we can integrate between these limits between Ti to T, isn't it? Correct. And right hand side we will have UA by MCP by T, isn't it? UA by MCPT, and here since this is divided by, you will get the integration. After integration you will get a log term, so that log you can take it on the right hand side, it will become exponential. Does it make sense to everyone? Hello?
Yes, sir.
So it is just matter of putting the values now. It is just matter of putting the values. So T naught is already 124, isn't it? 125. Temperature T is what? 80 degrees Celsius. That is what you wanted to achieve, isn't it? T naught is again 125. And what was the initial temperature? 24 degrees Celsius. And that should be equal to exponential of minus U is what? 171. That is what we have calculated, isn't it? 171.4. Area is 10 meter cube, 10 meter square. So that is already taken as it is. Mass is volume into density. Volume is already given 5 meter cube into density is given. Density is 870, isn't it? 870. So that will give you a mass into Cp. Cp value is already given 1.8 into 10 raised to power 3, isn't it? Multiplied by T. We can back calculate. We can back calculate the value of TF here, isn't it? This is TF. So TF comes out to be. Is it clear what we are doing, everyone? Is it clear what we are doing here?
Yes, sir.
So here mass will be rho into V. So that is 5 into 870 kg. So TF comes around, anyone? This should be the answer you are expected to get. Check whether it is correct.
Yes, sir. Approximately.
Approximately this is same.
Yes, sir.
So is it clear to everyone? Is there any question, any doubt? Please ask me. If there is something is not clear, please ask me. Okay. All right. Hello.
Yes, sir.
Now what is the second part? Part B is we have to calculate. We have to calculate the delta M, isn't it? That is part B. Correct. So what will be delta M? So how the heat transfer coefficient is defined? Let's say heat transfer HI. HI will be the heat transfer coefficient inside the container. So that will be given by what? Km, that is the thermal conductivity of the monomer divided by the film thickness inside the reactor. Do you all agree? Yes or no? If I go back and look at the system, this is the system. HI is already given 400, and inside there will be a film, isn't it? This film, and this inside monomer film which is there, that thickness we wanted to calculate. So inside heat transfer coefficient we already know. So inside heat transfer coefficient will be given by what? From the film theory. That will be given by thermal conductivity of the monomer which is there inside divided by the thickness of the monomer. Is it a monomer film, isn't it? So delta M, correct? Yes or no? Do you all agree?
Yes, sir.
So that is what I have written here, isn't it? In part B, that is what I have written. So HI will be Km by delta M, isn't it? And we wanted to calculate delta M. So from this delta M will be given by what? Km by HI, isn't it? Km value is already given. Km value is given as 0.25, isn't it? Divided by HI is 400. HI is 400. So you will get the film thickness as
So 0.06 centimeters.
625 meter. Is it correct?
Yes, sir.
Correct.
Yes, sir.
This is the part B, answer of part B. Now in part C, what is been given? In part C, if this inside monomer film is replaced by a film of water, let's say inside, I don't want it to heat up the monomer mass, but instead of that, if I wanted to heat up, let's say water, but I am keeping my heat transfer coefficient same, isn't it? So what will be the thickness of the film? What will be the thickness of the film? So I wanted to calculate thickness of the film if the monomer is replaced by water. So I wanted to calculate delta W. And what will be the delta W? That will be, remember delta W is defined as what? KW divided by HI, isn't it? Correct? Yes or no? This is kept same. This is kept same as monomer case. Now KW we can find out. KW is what? Thermal conductivity of the water. Thermal conductivity of the water, you can find out the tables given backside of the book. So in the book, if you look at backside, there are multiple tables are there in this book by B.K. Datta. So if you look at that at a particular temperature of let's say 80 degrees Celsius, you can find out what will be the thermal conductivity. Okay, so thermal conductivity of the water is given as, thermal conductivity of the water is 0.65 watt per meter degree Celsius, isn't it? That is what the thermal conductivity of the water is. Okay, so now from this we can, so this is given from table, backside table given in the book. Okay, so we can find out KW from the table given backside of the book. Backside. So you can put the values now, isn't it? 0.65. Sorry. I am sorry. For the same, okay, I'm sorry, I just missed. I'm sorry. This we wanted to find out. This we wanted to. HI will be what? For same thickness. Same film thickness as monomer case. Okay, so for monomer case we have already obtained as this value 0.000625. KW is 0.65 divided by HI. So calculate the HI. HI will be HI new. This will be HI new. So HI new comes out to be how much? HI new will be equals to anyone? HI new should come around 1040 watt per meter square degree Celsius. Is it clear? This is part C. Is it clear?
Yes, sir.
Okay. So this is the solution of problem 1. Now let's look at the problem 2. So again, let me just copy the statement of the problem 2 and we will again come back to this. Let me copy the problem statement here. Okay, so let me just okay. Now in this problem, what is been given is the steady state radial heat transfer profile of 10 centimeter diameter sphere is given. Let me just draw a sphere here. Then you will appreciate what I'm trying to say here. So let's say this is the sphere. This is the sphere. Please forgive me for not drawing it very accurately. So now in this particular sphere, what is been given is the temperature distribution with respect to the radius r. Let's say this is r. So T is given as 101.39 minus 1.389 into 10 raised to the power 3 r square. If I am not wrong, let me just check. It is r square. Yes, r square. Where T in. So the important part to note that T in degree Celsius and R in meter. Okay. Thermal conductivity of this metal is given as K is given as 12 watt per meter degree Celsius. ठीक है. Sphere is placed in the ambient temperature of 30. So this ambient temperature here T ambient is T ambient in this case is 30 degrees Celsius. Okay. T ambient here is 30 degrees Celsius. Correct. Now what we have to calculate is, so first question is what is the maximum temperature in the sphere? So what will be the maximum temperature in the sphere? Anyone?
101.39.
101.39, because this is what this equation is saying, isn't it? In this equation, if I differentiate this equation with respect to r, you will say that the slope is minus, isn't it? Slope is going to be minus, isn't it? If you differentiate this with respect to r, and that means what? Slope is minus means what? As your radius is increasing, your temperature is decreasing. That's what it means, isn't it? So clearly your maximum temperature will be at center when radius is 0. Do you all agree? Do you all agree?
Yes, sir.
Sorry. Maximum temperature will be present at center. Present at center. R equals to 0. Since dt by dr is negative, that is what? Temperature decreases with increase in R. So therefore maximum temperature will be present only at the center. Correct? Is it clear to everyone? The reasoning why we are giving this reasoning here. So the maximum temperature will be at R equals to 0. So that means T max will be equals to 101.39 degrees Celsius. Correct? Yes or no? Is it clear to everyone?
Yes, sir.
Now what is the second part in this question? Second part in this question is, do you think that there is a heat generation in the sphere? So what do you say on that? Do you think that there is a heat generation in the sphere?
Yes, sir.
Yes or no?
Yes, sir.
Why you are saying that the heat generation is there?
Sir, because the temperature at the center is constant, so there might be some source which might be generating heat.
So see here only the if you look at the outside of the sphere, there is a convective heat transfer is taking place, isn't it? So heat is taken away from the sphere. Remember the inside temperature here, maximum temperature is 101.39 degrees Celsius. Outside temperature here is ambient temperature is 30 degrees Celsius. And if you look at this rate of change of temperature along the radius, you can see that the temperature is decreasing as your radius is increasing. That means at the surface here the temperature is low, isn't it? So when you can have such type of system, such type of system you can have only if there is a heat dissipation is taking place outside the sphere. Do you all agree? Yes or no? And if there is a heat dissipation is taking place outside and the temperature has to be maintained, the center temperature has to be maintained at 101.39, definitely there has to be the heat generation. Otherwise it is not possible. Do you agree? Isn't it? This is the steady state temperature given, isn't it? That means the center temperature is not varying. It is going to be constant at 101.39 and there is a constant dissipation taking place outside the sphere. And if you look at the rate of change of temperature with respect to R, it is decreasing as your R is increasing. So that means there is a continuous dissipation is taking place outside the sphere. So continuous dissipation taking place means there should be a continuous generation. Then and then only the temperature here at the center will be maintained at 101.39. Do you all agree?
Yes, sir.
Yes, sir.
So that means when I can have the temperature here is maintained at 101.39. The only possibility is there should be a generation of heat, isn't it? So in part B, what we can say is, part B, what we can say is, center temperature is maximum and it is decreasing with radius, increase in radius, increase with, increase in radius. So that implies that heat is dissipated. from the surface. By convection. So that means what? Heat loss is there, isn't it? Heat loss from sphere. And if there is a continuous heat loss from the sphere, that means what? In order to maintain the center temperature, there should be a, in order to maintain there must be a heat generation source. In the sphere. Do you all agree with this reasoning?
Yes, sir.
Since there is a continuous loss from the sphere, if you don't generate, what will happen to the temperature? Temperature will keep on decreasing. But we are saying that at steady state, it is constant. It is not changing at the center. Temperature is constant at 101.31, isn't it? 39. So that means what? There should be a, definitely there is a heat generation required. Otherwise, it is not going to be true. Correct? Now, what is part C? In part C, what we have to calculate is, in part C, calculate the, okay. So in part B, do you think the heat generation? Yes, there will be a heat generation. But then the next part is by what rate? By what rate? So we have to calculate psi V. We have to calculate psi V. So how we can calculate psi V? So rate of heat loss from the sphere, what? The rate of heat loss from sphere. Rate of heat loss from the sphere will be given by what? That will be given by Q, and Q will be given by
K dt by dr.
4 pi r square, that is the area, into flux, isn't it? Minus K dt by dr, and that is calculated at R equals to R. Do you all agree? So this is the amount of heat loss from the sphere by conduction at the surface. Yes or no? If this is the sphere, if I draw a sphere here, what will be the heat loss here? What will be the heat loss here? Heat loss here will be area here. The area will be 4 pi r square at this surface conduction, isn't it? Into the flux here, and flux will be given by minus K dt by dr, isn't it? Do you all agree?
Yes, sir.
Yes or no? Now dt by dr at R equals to R, that we can calculate. So remember, the temperature distribution function is given. So you can differentiate that with respect to R. What you are going to get is minus. So equation is 1.389, isn't it? So I'll just write down in terms of 1.389 after differentiating into 10 raised to power 3. R square is there. So differentiate with respect to R will be into 2 R, and that has to be calculated R equals to capital R. Do you all agree?
Yes, sir.
So that means what? This will be given as minus 1.389 into 10 raised to power 3, 10 raised to power 3 into 2 into R is what in this case? What is the diameter? Diameter given is? Diameter given in this case is
10
centimeter. So radius in the meter will be 0.05. So this comes out to be, this value comes out to be, if you calculate this 138.9 degrees Celsius per meter, isn't it? If you put it in this equation, the above equation, so Q you can calculate now. 4 into 3.14 into r square is 0.05 square into into k is, in this case, k is what? K is already given, so k value is given as 12, isn't it? Right? Into 138.9. That minus sign I have omitted because this is the heat loss, but how much is the heat transfer? I wanted to calculate that minus sign. I can, get rid of, isn't it? Correct? I am calculating the heat loss. That's why that minus sign is coming here. Do you all agree?
Yes, sir.
Okay.
Yes, sir.
So anyway, this is minus sign here, isn't it? That this minus sign get cancelled out. This becomes plus. Correct? So this Q comes out to be, if you calculate that, this comes out to be 52.36 watt. This is the heat dissipated. Heat. So this is the heat conducted at the surface, and this heat conducted at the surface should be equal to heat dissipated. Correct? The total amount of heat that is being conducted at this surface will be same as the amount of heat taken by the convection here. Do you all agree? Isn't it?
Yes, sir.
Also, it should be same as this total amount of heat dissipated. Here there is no heat coming in, isn't it? So this amount of heat dissipated should be equal to the amount of heat generated also.
Yes.
Isn't it? In order to have a steady state. Correct?
Yes, sir.
Do you all agree?
Yes, sir.
So this should be dissipated from surface by convection, and this is also same. This is also same as heat generated in the sphere. Okay, so now we can calculate the psi v here, because Q is given as 52.36 and this should be equals to volume into psi v, isn't it? That is what the heat generated in the sphere. The volume of the sphere will be what? 4 by 3 pi r cube, isn't it? Pi r cube into psi v. So 4 by 3 into 3.14 into r is 0.05 cube into psi v. You can back calculate the value of psi v. Do you all agree? Yes or no?
Yes, sir.
So this you will get around 100 into 10 raised to power 3 watt per meter cube. So this is nothing but the volumetric rate of heat generation.
Why are we defining it as volumetric heat rate generation? I mean, the
So
question.
we are defining this as a volumetric rate of heat generation because we are assuming that the rate of heat generation is uniform throughout the volume. That's why it is defined in terms of volume.
Okay.
Do you agree?
Yes, sir.
Okay, all right. Now what is the part C? Part C is, if I go back to the question, part C is calculate the film coefficient at the outer surface. So that is also easy, isn't it? That is also easy because what we are assuming that the rate of heat transfer is same as the heat dissipated outside, isn't it? So Q is same as heat dissipated outside, heat by convection. This is what we have said, isn't it? So that means what? This is nothing but HA T surface minus T ambient. Do you agree? Do you agree or not? Isn't it? And T surface we can calculate. T surface will be what? T surface will be nothing but 101.39 minus 1.389 into 10 raised to power 3 r square, and here we have to put r equals to capital R. That is going to give me TS. Do you all agree?
Yes, sir.
So 101.39 minus 1.389 into 10 raised to power 3 into 0.05 square. So what we get, T surface in this case is going to be, T surface comes out to be 97.9 degrees Celsius. Check whether this is correct. Okay. Now we can put it in the original equation. So original equation Q is again given as 52.36, isn't it? And that should be equals to H into area. So area of the sphere is again 4 pi r square. Just a minute. Hello. So I will be joining in 10 minutes. I'm in a class. Okay. So 0.05 square multiplied by, this is the area, isn't it? This entire thing is area multiplied by TS. TS we have already calculated, that is 97.9 minus ambient temperature is already given in the problem. So ambient temperature in the problem given as 30 degrees Celsius, isn't it?
30 degrees, sir.
So we can calculate this. Okay, so let's not make it confusing. Okay, so this is nothing but area, isn't it?
Yes, sir.
So we can calculate H. So H comes out to be, anyone? You should get around 23.34 watt per meter square degree Celsius. Check whether this is correct or not.
Yes, it's approximately correct.
Okay. So is it clear to everyone what we are doing?
Yes, sir.
Yes, sir.
Okay, then is there any question so far?
Sir, I have a small doubt, not related to this exactly, but like supposing in the quiz, etc., or maybe the in minor, etc., what is the margin of error? Like supposing like in this question, it's 23.34 is the answer.
Don't worry about that. We generally keep it for reasonable tolerance. Okay.
Oh, okay, sir. Thank you.
Okay. So can we stop here unless you have any question to ask?